So let's do a quick review of what we did yesterday. Um, yesterday we started talking about the whole concept of modeling, why it's needed, what the benefits are, and we mentioned also that a model essentially describes how the system behaves over time. That is the essential information that it captures. And we went through three examples so far, three or four. How many did we look at? So we looked at the fluid flow example, we looked at the car speed or a moving mass speed example, we looked at the heat transfer example. And I think the interesting feature was the similarity of all of these systems when it comes to their model. Even though their appearance, the physics behind them, how they work are different, the way they behave is similar. And you can tell that by, if you have the model, if you didn't know what the physical system was, if you simply had the differential equation describing the model, you could see that all of these systems are, what do they have all in common? What is one common feature of all of these systems when it comes to their model? The differential equation is first order. That's feature number one. And therefore, these systems, by the way, are called first order. Because their differential equations are all first order, these systems are all first order systems. So we have looked at three first order systems. Now, when a system is first order, as soon as we know that, we know a lot about that system when it comes to its behavior. So we saw that a system that was a fluid tank behaved the same way that a car worked and a heat transfer system worked. So speaking, I think isn't there where we stopped last time? Okay, so let's, again, as a way of review, try to find the steady state temperature. Try to find the steady state temperature for this system. For this system, if we have a constant flow of heat coming to the system. So what we are trying to solve is if so the question we have, if Qn is constant, which means it's not going to change with time. So we turn on the heater and we don't touch it. We let it continuously supply the same level of heat as the system works. The question then becomes, what is T steady state? Now, a steady state means it's not going to change anymore. You've seen with all of the previous two systems that with a constant input, the output of the system converges to a constant value and stays there. Haven't we seen that for other systems? And by the way, that value did not depend on the initial condition. Do you remember that? So it didn't really matter where the system started. The steady state value of the response was always the same. So let's just make sure that we have this new definition. So we talked about just now about the steady state response. So we talked about steady state response. We've shown already that steady state response exists for first order systems. And if you give the first order systems a constant input, regardless of their initial condition, they would converge to that value. So our question is to find that temperature steady state. So where do we start to find a steady state temperature? What is the tool that we have to deploy? Do we look at the picture of the system? Do we scratch our head? Two options so far. Do we go out for a walk? The third option. Or do we look at the model of the system? I see a few nods, so probably we will look at the model of the system. Why? Because the model of the system just went off on its own. The model of the system basically captures how the system behaves, including in its steady state, including when the response is no longer changing. So let's go ahead and rewrite the model. So what did we have? Let me go back. So the model was theta dot theta. We defined theta, by the way, as temperature minus the temperature outside. So the model we had was theta dot was equal to 1 over m times c, where m is mass of the fluid inside, mass of the air inside that volume. C is, what is C? C is? It's a constant, it's called specific heat. So essentially it captures this information. How much heat does it take for 1 unit of mass to increase its temperature by 1 unit? That's the information. And it's different for different materials. So it's a material property. Okay, so we had 1 over mc multiplied by qn minus h times a times what? Times theta? Is it? Let me double check. Yes. Okay. So this equation tells you how theta changes over time in response to what? Remember, theta was what of the system? Theta was two things for this system. One, it was theta was what for the system? Theta was the output for the system, but equally importantly was its state variable. So theta was two things for this system. Theta was its state variable as well as the output for the system. So when you look at this differential equation here, it tells you how output of the system changes in response to what? What causes the change in the output of the system? In response to existence of the input as well as initial condition. As well as initial condition, because again, the model describes the behavior under any possible conditions, including, imagine this case, that you somehow heat up this chamber and turn Q off completely. What will happen over time if the outside temperature is lower than in the inside temperature? Over time, it will cool off until what happens? Until temperature of inside and outside are equal. Can this model describe that situation? It can. If you let Qn be equal to 0 and theta be a positive number, which means theta is a positive number, which means temperature of inside is more than temperature of outside. If that is the case, what does this model show? The model shows that theta dot is what? Theta dot will be negative. So it shows that theta dot is going to be negative. Now, theta decreases until what happens? Theta decreases until until, look at the model. All the questions I'm asking you can answer by just looking at the model. Until what happens, theta dot will decrease. When decreasing theta dot will stop, according to the model? Of course, theta dot has to reach 0, but when will that happen? Remember, the condition we are simulating is where Qn is equal to 0. So we have some initial value of theta, non-zero, which means temperature of inside is more than temperature of outside. If that is the case, if you let this system be on its own, what will happen in this system is that theta will start decreasing. Until when? What stops theta from decreasing anymore, according to the model? There is a specific time, but if you look at the model, when will theta dot become equal to 0? That tells you that theta no longer changes. Can you see that? Okay, when will that happen? Absolutely, that's the key point. Now, this is very obvious for this system. You don't need the model to tell you that. But we are taking these steps to draw general lessons what we can do with models. So if you come across a system that, generally speaking, we are not as familiar with circuits, that I'm not advocating this. We should all know about circuits because more and more systems are multidisciplinary. So you have mechanical elements, you have electrical elements, you have logics involved, you have control involved in all the systems. But generally speaking, we don't feel as much what happens in a circuit. So the benefit of knowing all of that is when you have an equation for the circuit, you can draw similar conclusions. You can talk about what is the steady state voltage, what is the steady state current, will it go down, will it go up, just simply by looking at the model and understanding how a differential equation can convey all of that information. Okay? Was that a good enough wake-up call? So that tells you when you come to the class, you should have already reviewed for at the minimum what we have covered last time, plus read the textbook and whatever is assigned as the reading material. So let's go back to what we are doing here, which is what? Which is finding the steady state response is if Qn is constant. So for finding a steady state response or equilibrium, we put theta dot equal to 0. So if you set theta dot equals 0, which is the condition at steady state, comma, equilibrium, then what you know is Qn minus HA theta has to be equal to 0. We know Qn is constant. Now, this is theta steady state, theta that no longer changes. So once we write this, then you can find theta steady state to simply be Qn, the level of heat that comes in, divided by HA. Divided by HA. Now, remember, Q is temperature minus temperature of outside. So this temperature then it is going to be a steady state temperature. This temperature of inside in steady state minus temperature of outside is going to be Qn over HA. So when you look at this equation, what lessons can you quickly draw? Observation number 1. Observation number 1. Steady state temperature doesn't have anything to do with what kind of fluid you have inside the chamber. So you don't see any effect of M or C, which is how much fluid you have, M, mass of fluid, or its heat capacity. So in steady state, those play no role. Can you see that? However, what plays a role, first of all, is how much heat you put into your chamber. The higher the level of heat continuously coming to the chamber, the higher the steady state temperature would be. That is expected, right? in reverse relationship is H, which is what? What is H, by the way? It's the convection coefficient. So if you have more convection, what will happen to your steady state temperature? It would be a lower value. So if you're losing more heat, so you could lose heat due to convection due to two things. One, if H is high. The other one is if the area of the chamber is too high. So you have more area to lose heat through, then that also drops the steady state temperature. Okay, so go ahead and plot the response. Plot T, not theta. Plot T. Theta is a trick that we play to simplify the model, to get rid of T infinity, to get rid of carrying T infinity around throughout writing the equation. So I want you to please go ahead and plot the response for this system. So we're talking about capital T, which is temperature of the chamber versus time. And imagine there is an initial value. We call it T0 or T initial. I know we use T0 for equilibrium, but T0 is more appropriate for the initial condition. So we are going to use steady state going forward for a steady state value of the temperature. So if I can get it to right here. So T, oh, not. So T0 for initial value of T. So let's say this is initial value of T. So depending on what value for Q in we have, we'll have one value for T steady state. So let's say this is value of T steady state. The way to get to a numerical value is by knowing the value of H, value of A, and knowing Q in, and also T infinity. So we need to have four numbers in order to calculate a number for T steady state. But what we know is that this will start from initial value of T and gradually will rise and will settle at T steady state. Now, how quickly will it do it depends on, so the speed of system. The speed of system, it depends on two variables. Can you tell me what those two variables are? How fast theta changes, or rate of change of theta, which is expressed by theta dot. What defines that speed? If you look at your differential equation, H and A are multiplied by theta. So what defines the rate of change of theta, which is theta dot, is it relates to H and A, but also relates to M and C. Can you see M and C multiplied? We'll put this all into one formula shortly, but that's the defining factor. Okay, so so if you want to plot, it starts from this number gradually goes up and settles. Now settles at t steady state, so it should go all the way to here and settle. And it's a smooth transition. So I didn't do a good job drawing this. Let me try one more time. So it settles. It doesn't change after reaching steady state value. So start from the initial condition and settles. And by now you know if the initial condition is different, that portion that the response is changing would be different. By the way, that portion when the response is changing is called the transient portion of response. So let's take that down also. So we now know that response has two sections. It has the transient, plus it has, what is the second portion of the response that we already discussed? It is called? Exactly. The second portion is called the steady state portion. Now when you look here, steady state portion is this portion. The portion that response no longer changes. It has reached a number and it stays there. That's called the steady state portion of the response. Transient portion, however, is the portion that does change. So starting from t0 all the way to here is the transient portion of the response. Okay, so if you want to identify this portion, would be the transient portion. And anything from here onward is the steady state portion of the response. Okay, so we discussed it last time and we showed it with other examples, but it's also applicable here that if the initial condition is something different, what will happen? What portion of the response would have a different shape? Is it the transient or steady state? The transient. So if the initial temperature is something different than what the T naught that I'm showing on the plot, what will happen is the transient portion of the response would be different. Again, the rate of change would not be different. The speed of the system would not be different because initial condition has no effect on the speed of the system. The speed of system is defined by m, c, h, and a. What will be different is the shape of the transient. So if initial condition is exactly equal to t a steady state, what will happen? If t naught is exactly equal to t steady state, what will happen? There is no change in temperature. There is no change in temperature. Why? Because Qn over HA is equal to that the theta. So it will make what is inside the parenthesis equal to 0, which means theta dot is equal to 0. And if your T naught is above T steady state, it simply decreases, or the temperature will go down, even though the heater is on. Even though heater is on at the same level, the temperature will go down, and that is what will happen. Okay, any questions before we go forward? So you feel comfortable with getting to write first order differential equations. Great. So let's now look at another example. And these are analog electric circuits. We come across these systems, we need to know how they behave. In other words, we need to have models for these systems. And when it comes to analog circuits, there are a few common elements. We have resistors, we have capacitors, and we have inductors. So let's look at, just as a way of review, quickly look at each of these elements. So if you have a resistor, the basic behavior of a resistor is that its voltage is proportional to its current. V is equal to R times I. That's essentially what that equation says. So the amount of potential across the resistor defines how much current will pass through it, and the amount of current is proportional to value of resistance. So if you have more resistance, so with the same voltage, if you have more resistance, less current will pass through it. If you have less resistance, more current will pass through. That's what it says. Now, in other words, a resistor, an ideal resistor, is it a dynamic system? Do you remember the definition of dynamic systems? What was the definition of a dynamic system? Yes. Absolutely. So if you consider a resistor as a system with its input as the voltage and its output as a current, you can imagine that, right? So you attach a battery and you measure how much current passes through it. You just put a multimeter to it through the circuit in series, and you measure the current passing through, right? Okay. So based on what you see on the board, which is the relationship between voltage and current, is a resistor a dynamic system? In other words, would there be a delay between the time you turn on the switch for this current and between the time that you turn on, so the voltage is applied, which is the input applied, and the time that you would read your current? Would there be a ramp like what we have seen in the temperature or the level of fluid or the speed of the car? And the only tool you have to answer the question is this equation on the board, Ohm's law. What does Ohm's law say? Does it say there is a delay? So you say no, but what tells you there is no delay? The fact that time is completely absent. There is no differentiation involved. There is no differential equation involved. So it simply says, tell me what the voltage is, and the current is simply proportional to that. There is no delay. Now, of course, this is an ideal resistor, an electrical element that just behaves like a resistor. There is no capacitance in it. There is no inductance in it. But in reality, a resistor is not ideal. A resistor would show some capacitance, for example, or will show some inductance, which are the next two elements in an electrical circuit, and those two elements are dynamic elements. Now let's look at a capacitance. So what this tells you, for a capacitance, it tells you the current is, for a capacitor, the current passing through a capacitor is equal to C, its capacitance, times derivative of voltage applied. Times derivative of voltage applied. So just simply looking at this equation, if current is the input and voltage is the output, you can see that the voltage wouldn't immediately jump. The rate of change of voltage is proportional to the current you apply, so there is a delay. Can you see that by just looking at that equation? And an inductor with inductance L is similar. So now here the relationship changes. So if the input is voltage, and the output is current, the rate of change of that output is proportional to the voltage. Can you see that? The rate of change of current as the output of an inductor is proportional to the voltage you apply. So it's not an immediate jump in the current. The current gradually go up and will reach a steady state value. Okay, all right. And we know you don't have a capacitance just by itself or a resistor by itself. They're connected to form what we call RLC circuits: resistors, capacitors, and inductor attached to each other to do functions for us. So how do we write equations for that? Remember how we wrote equations for other systems. What did we do? We said, okay, we need to know the law that governs this system, and we will capture that law by an equation. So we did it for mechanical systems through what law? It was linear momentum conservation, which is also called Newton's second law. For heat transfer system, we captured it by what was the law of physics? Energy conservation. And for a fluid flow, we captured it with conservation of mass or volume. Here, there are Kirchhoff's law. Essentially, they're conservation of energy again, electrical energy in this circuit. So Kirchhoff's law says there are two laws that are essential for us. One, do you guys remember it from any other course before? Kirchhoff's law? Or how do you write equations for circuits? So if you know, it's good. So don't feel bad that you know it. So do you know it? I just need to know how much detail you need. So there are two laws. Law number one is absolutely. So so there are two laws. One of them says if you have a branch, like where? Like here. So if you have a branch like this, or I'm sorry, a node like this, which has two branches going out, one branch coming in. So the first law says at this point, current coming in will be equal to current going out. So you wouldn't lose current. So if I1 is coming in, so let me draw another branch here. So if you have a branch, or I keep calling it a branch, and a node like this. So if I1 is this and comes to this node, and I2 is here, the current passing through this branch, and I3 current passing through this branch. So we have a node. One connector brings current in, and two are taking out. What is the equation that we can write? The equation is, we are saying the current will not disappear. Basically, what comes in is equal to what goes out. That's law number one or two. The number is, so this is Kirchhoff's current law. There is also a Kirchhoff's voltage law, and the voltage law says if you have a circuit, no circuit can exist if it is open circuit. It can exist, but it wouldn't function. It wouldn't carry anything. So when you have a closed circuit, which is all circuits, like this one. So we have a source of voltage. This is EI, which is a voltage applied between these two nodes. And in this case, you have a resistor and a capacitor. This forms a circuit. It forms a loop here. The voltage law says if you go around this loop and add all the voltages, what will happen? They will become equal to 0. Become equal to 0. Now, if you have a source of voltage, it's a positive voltage. If you have voltage drops, these would be negative voltage. And that's how, when you add them up, they become equal to 0. So I'll show you another example. So the other, the other law, the second law, Kirchhoff law, says if you add voltages around a circuit, it becomes equal to 0. Okay, so let's look at this example and apply those laws. The objective is what? Why are we doing this? What is the end product that we are after? Remember, we said the first section of this course is about modeling. So we want a model. We want a model for this system. The model predicts what? Behavior. So it tells you how the output changes over time. The model tells you how the output changes over time. That's what the essence of a model is. And we know that model would be a differential equation. So the input for this system, what causes change in this system, is this voltage V1 that is applied between these two nodes, plus minus, which will cause a current passing through this circuit, and the output is the current. So we want to know how current changes over time if we apply a voltage between those two nodes. And we know that it is a dynamic system. It is not that as soon as you flip the switch on and start applying the voltage, the current will go immediately to a value and stays there. It would be a gradual change. So it's a dynamic system. What element causes this system to be a dynamic system? The capacitor, exactly. Very good, thank you. Okay, so let's go ahead and apply the Kirchhoff's law for voltages. So the law of voltages, so we are going to use Kirchhoff's law of voltage. That's the fundamental law we are going to use. It basically says voltage 1, which is source of voltage, plus voltage drop across the resistor. What is the voltage drop across a resistor? Let's go back. What is the basic equation for a resistor? Voltage across it is equal to R times I. So it would be, we capture voltage drop with a negative sign, so minus R times I. So we got that. Now let's go to the capacitor. What is the basic equation of a capacitor? Let's go up again. The capacitor equation is I is equal to C times dV over dt. Okay, what we are after is voltage drop across the capacitor. So this form is not as useful. So I need to know what is the voltage in terms of the current, not what the current is in terms of voltage. So how can I get to that? By knowing this is the basic equation. Absolutely. If you integrate this equation, you get voltage in terms of current. So let's do that. So if you take this equation, let me see if I can do it right here. So if you integrate this equation, it would be integral of I with respect to what? What is the variable of integration? With time, absolutely. Time is our independent variable. So I dt is equal to C times V plus a constant. Every time we integrate, there is plus a constant. Okay, so what is V equal to then? So if we choose proper initial condition, we can eliminate that constant. So what is V equal to then? Absolutely. So it is, so the voltage drop here would be minus 1 over C integral of I d time. And that is equal to what? So you're adding voltages and voltage drop. That's equal to what? According to Kirchhoff's law. It is 0. So it says if you go around a closed circuit and add voltages, they have to add up equal to 0. Otherwise, you're saying voltage comes from somewhere. Basically, the law says voltage doesn't come from anywhere other than your sources and then the drops due to loads. So that adds up to being equal to 0. Okay, this is a bit of unusual equation, isn't it? So far, we didn't have an equation that had integral. We are more used to seeing differentiation, a differential equation. So what we can do as the next step is to turn this to a differential equation. How can we do that? How can we get rid of integral? Yeah, differentiate it. So we can differentiate this equation with respect to time. So it becomes d v1 with respect to time minus r is a constant, so I'm not going to differentiate it. So it's going to be r di over dt minus 1 over c again is a constant, so it just stays. What is time differential of integral of I with respect to t? What is d over dt of integral? So a side note here, let's review that. So d over dt of integral of I dt is equal to what? It is equal to I. How do you know that? You can simply look at it this way. dt and dt will cancel each other, and d and integral will cancel each other. So d is reverse or opposite or inverse of integral. So the end result is simply I. So here, this becomes I equals. Okay. So over time, we have every time we develop a differential equation, we took it to a special format. We can try to do the same thing. So I'm going to keep di over dt because we decided I was the output of the system. So change of output of the system is going to be equal to 1 over r multiplied by dv1 over dt minus 1 over ci close bracket. Let me remind you that for a tank, we had h dot was equal to 1 over a wn minus 1 over ch. Do you remember that? This was model of what? The second equation that I have, the equation at the bottom of this slide. This was model of a tank of fluid, which has no resemblance to a circuit made of a resistor and a capacitor. Did I write the equation correctly? Let me double check to make sure. No, it's C over H. I apologize. C times H. I apologize. I made a mistake in the last portion. So let me erase this. So what acts as an input to this system is not the voltage itself, but its time derivative of voltage. If you compare it to the fluid tank system, it's d1 over dt that acts like W and what causes the voltage. So in other words, if voltage is stationary, if voltage doesn't change, if we attach a battery which can provide, at least in theory, a constant level of voltage, and there is no current at the beginning, would current change at all? According to this equation, it would not. And that's a property of a capacitor. You need fluctuation in voltage in order to get any current to pass through the system. And that is insight that may not be obvious. But you can get that insight by looking at the equation for the system. So it's d over dt that acts like an input, that acts like a change, a cause for change in the system. Okay, so what is the state variable here? State variable, everybody? Current is the state variable. Input is d1 over dt, and output is also the current, the purpose of modeling, what we try to capture. Okay, so if you want to summarize in a way everything that we said, essentially we said differential equations represent behavior of dynamic systems. We didn't qualify these dynamic systems, but everything that we discussed so far are going to be classified under linear dynamic systems. So all the equations that we had never had power in them or square root or anything that is nonlinear. So every equation that we had for electric system, for heat transfer system, everything, including the drag force applied on a car. We said the drag force was linearly proportional to velocity. Do you remember that? Let me show you one more time. Here, look at the force. Let me show you the free body diagram. We had a force, capital F, that was pushing the car forward and a force that slowed it down. We made the assumption that the force that slows down the car is simply proportional to velocity. That's where we made the system to be linear. If we said, for example, that the slowing force or the drag force was proportional to v squared, that system no longer would be a linear system. So the differential equation would not be a linear differential equation. This is the typical response. You plotted it before I had it on the slide. This is the typical response of a first order dynamic system. It starts from an initial condition and converges to a steady state value of the output. And we talked about the transient response as well as the steady state response. We haven't yet talked about free response versus forced response. Free response and forced response is another characteristics of the response. Now, the best way to imagine a free response is this. Go back to the very first system that we discussed. What was the very first system we discussed? It was the fluid tank, this system. Free response is when there is some fluid in the system, but there is no input coming to it. There's nothing that forces any change in response. So if there is no input to the system, that the response is called free response. In existence of input, the response is called forced response. That's it. That's the definition. So let me go back here. So you can see it on the slide. It says free response. In terms of differential equation language, it's called homogeneous response. Homogeneous means the right side of the equation, the forcing function is zero. So it's also called free response, homogeneous, zero input. You see in the parentheses, it says zero input. So when you have no input to the system, the response, the behavior of the system called free response. Free response. And you also have forced response, which is when an input actually exists. So here's your assignment, in-class assignment. So grab a piece of paper and plot the free response of the tank. Free response of a tank. So we are after what? We are after free response of the tank system, which essentially means you have the tank, C cross-section area A, and it initially has some fluid in it. If it's completely empty, the response is obvious, right? If it is completely empty, Of course, it remains empty if you don't have any input to it. But the assumption is that you have some fluid. So if H is the level of the tank, H at time 0, H at time 0 is equal to H naught. So you have some fluid in the tank. Okay, so let's look at the equation one more time. The differential equation is H dot is equal to 1 over A W N minus C times H. Oops. That is the model. That's how this system works. So what do we know? We know what is 0 already. We know there is no input to this system. So Wn is 0. So in absence of an input, what do we know about H? Let's start with H dot. What do we know about H dot? Absolutely. H dot is going to be negative C over A times H. Which tells you what? What does it tell you about the rate of change of H? What is value of H dot? It is negative. We agreed on that. Tell me more though. Do we know value of H dot? If I give you numerical value for C and a numerical value for A, do you know value of H dot? Some say no, some say yes. Why do you say we don't know it? What is missing? So you're saying, in other words, that H dot depends on H. So as H changes, H dot value changes too. But don't we know value of H at time 0? So we know the value. We know how much fluid is in the tank, right? Okay? So at time 0, we know H dot is a negative number, and we know exactly what that negative number is. So basically, you fill the tank, you let it go, what will start happening? The level of the tank will start dropping. And as the level of the tank drops, what happens to H dot? Its value, its absolute value, gets smaller. So the rate of decay, the rate of decrease of the level of the tank itself goes down. Can you see that? So the speed by which H changes, the speed of H changes. It becomes a smaller number, smaller number, smaller number. Eventually, H dot becomes equal to 0. And when is that? When H dot will be exactly equal to 0? Look at the equation. When H is exactly 0, when the tank is empty. Okay, so if you want to plot the response, how will it look like? Looks like this. So it starts from H naught. This is H naught value. And goes to 0. And it's an exponential decay. It's an exponential decay the same way that the rise of this, when we had input, when the response was a forced response, the rise was also exponential. And if you put both free and forced responses on top of each other, you would see that the rate of change is very, very similar. So if we now combine this, so I know this is free response. So this was our free response. Now, if we look at the forced response, we already know if we apply a constant level of fluid to this, it will gradually go up and settle at a value. So if you combine the two responses, so let's say this is for a given value of Wn, let's say this is H steady state. And let's further assume that the initial condition is exactly the same. So the tank this time starts at the exact same value, H naught, but this time instead of letting it freely empty out, we are also turning the valve on, so we're giving an input. So what will happen? What will happen to the response? And imagine that Wn is high enough that will cause the level to rise. I'm already giving you H steady state, which is higher than H naught. What will happen to the level? It will increase. Now, what I want, the most important message is this, that the time that it takes for both systems, free and forced, to reach their steady state value is exactly the same. That's what I want you to recognize and always remember, that the speed of response is determined by the dynamics of the system and not by how much what is the level of initial condition or how much fluid am I letting into the tank. So those do not define the speed of response. The speed of response simply is defined by A, which is cross section, and C, which is how much we are opening the orifice at the bottom. So it doesn't have anything to do with H naught or with the level of Wn, the speed of system. So this is, if you want to take one lesson away from this class, that should be it. That the dynamics of the system is not defined by the level, the numerical value of input, or numerical value of initial condition. It's an inherent behavior. It's built into this tank. So it doesn't matter how much I fill it up at the beginning or how many turns I open the faucet. Okay, so let me try to plot this. So it will start. So I can go maybe from the back. So steady state. Now, this is not the response because I can't draw on the previous line. I will do this. Here's the response. Now, again, it's not linear. It's an exponential change. But the most important lesson from this is the time that it takes for the system to go through its transient portion of the response is always constant. It is always the same for the same system. It doesn't matter if the response was free or was forced. It doesn't matter whether the initial condition was 1 unit or 25 units, or was negative 5 if a system can have a negative initial condition. So the speed of response and the time that it takes for the system to settle does not depend on value of input or value of initial condition. And you've seen it also in the past. You started from various initial conditions, and it took the same amount of time to reach steady state. Okay, so let me write this down. Let me see if I can write this down so we can capture. So we are talking about speed of response Or in other words, time to reach to reach steady state does not depend on values of input or initial condition. So it's the characteristics of the system. In other words, the time that it takes for the system to settle, it's the characteristics of the system. So in the case of the tank, it depends on values of A and C. So in the example for the tank, speed is defined only by A and C and not by H naught or Wn. They have no bearing. H naught or Wn do not define the speed of response. In other words, if you plot the response for a completely different value of Wn, what would change is the steady state, the value of a steady state response, but its speed will not change. Okay, so I'm going to challenge you to come up with a series of responses. So assume that the system has the same initial condition. So H naught is not going to change. Draw the response of the tank for increasing value of Wn. So assume at the beginning Wn is 1 unit, the next time is twice as much, and the last time is 3 times as much. Go back to your model, write the model, and solve these 3 cases. So the 3 cases that I'm asking you to do is this. Let me write it down. So what I'm asking you to do is plot the response of H as a function of time, which is level of the tank, when for this case, when H naught is H at time 0, okay? But input, so Wn is equal to 3 different values. Let's just give it numerical value. 1, 2, and 3. Or maybe make it 4, so each time is twice as much as the previous case. So I'll give you a minute to solve this problem. Okay, so we need to have the equation handy. So I'm sure you've written it, but let me do it also here. So what we have is h dot is equal to 1 over a wn minus c times h. So when wn is 1, what is h steady state? When wn is 2, what is h steady state? And when wn is 4, what is h steady state? So we need to know that. So how do we find h steady state? What is the technique? I'm listening to you guys. Why? That's the definition of steady state. No change. So means h dot is equal to 0. So if you set h dot equal to 0, you get wn is equal to c times h steady state, right? So what is value of h steady state when wn is 1? H steady state is equal to, again, I'm waiting for you guys, 1 over c. As simple as that. It's 1 over c, and wn is 2. It's, what is the value of h steady state? Did you say 2 over c? It's 2 over c. Be louder, please. So when wn is 4, what is h steady state? 4 over c. So what do you see here? As the input doubles, what happens to h steady state? It doubles. And that is a significant and important property of linear systems. You double the input, the output doubles. You double the input, output doubles. That's a property of linear systems. That's a beauty of linear systems. So from that, you can see as input so if how should we capture this in general? So there is a so this is a linear system, which means when u as input becomes twice as u1, the conclusion is y becomes twice as y1 when u is input and y is output. Clear what we are saying here? That's a property of linear systems. So you double the input, the steady state response will double. So that's one. We also know that speed of the system, the way h changes, is defined by c over a. The ratio of change of h is defined by that. So it means if you plot the response So we're handy. So accept that these as straight lines. So h versus time. So for case number 1, this is h steady state. The second case is double as much, and the last case is double as much. Do you see that? So h steady state each time doubles. However, the speed of response is the same, which means the time that it takes for the first system to settle, the time that it takes for this first system to settle is the same time that it takes for the second system to settle, which means it takes the exact same amount of time, and the same case here. So again, these are our straight, smooth lines, exponential rises, but the time that it takes for the system to settle doesn't depend on how much input you put it on. And it doesn't also depend on initial condition. It doesn't depend on either of the initial condition or the level of the input. So this is all H naught and system. So we have so far looked at 4 different physical systems: a fluid flow, a motion, a heat transfer, and electrical system. All of them could be written as a first order differential equation, and all of them would have this form. If x is your state variable, if you forget that each time state variable is the level of the tank or the current, just write it as x. And that's a common variable for indicating the state variable. If you do that, a first order system, the typical first order system, can be written in one of these 2 forms. A constant times x dot plus another constant times x is equal to input. Do you see that? Let's just look at one of the very recent examples that we just looked at. It was what? It was h dot is equal to 1 over a Wn minus c times h. Okay? So if you want to bring it to this form, if you want to bring this differential equation to this form, can you do that? You just bring ch to the other side and multiply both sides by variable a to get rid of that denominator, because there are 2 standard forms. One of the so in both of these standard forms, u input, which is in this case wn, is not multiplied by anything. So you can do that by simply moving terms around and multiplying by things. Now, this is a very important form. If the coefficient of x is 1, that's the key form. If the coefficient of x is made to be 1, the multiplier or the coefficient for x dot is a very important variable, which we show with capital T, and it's called the time constant of the system. So if you take your equation and into the second form, if you take any model you have into the second form and which means make the coefficient of x 1 to be equal to 1, the coefficient of x dot is a very important property of the system called time function. So as your first practice, go ahead and find time constant of the fluid tank. What is the time constant for the fluid tank? So time constant of this system. What is the system? H dot is equal to 1 over A Wn minus C times H. What is the time constant of this system? Do you need to see the standard form one more time? This is the standard form. It is Tx dot plus x is equal to input. For now, let's set aside the fact that there is a U disturbance. I'll explain about it in a minute. For now, just assume there's one U. So the form that I'm asking you to take your equation to is this. T x dot plus x is equal to U multiplied by, or let me be consistent with the previous form, divided by B, where x is state variable and U is input. So what is the time constant for the fluid tank? A over C. So let's give it a try. So what do we do to take it into this equation? We'll multiply both sides by variable A first, right? So A times H dot, and is it going to be equal to Wn minus CH? Take everything to the same side, so AH dot plus CH is equal to Wn. Now what we need to do, in our case x is H. What we need to do is to make coefficient of x to be 1. That's the key point. So you need to divide by C. So A over C H dot plus H is equal to 1 over C Wn. So from here you can see the time constant is A over C. Now for every first order system, we know the shape of response to a constant input, don't we? Already we know that the shape of response to a constant input looks like this. Now what is the significance of T? T as time constant is the time that it takes between initial value to get to 63% of the final value. Now, final value for this case is what? Can you read the numbers of it? 10. So 63% of 10 is what? 6.3. So the time that it takes to get to 6.3 is roughly here. So it means the time constant of this system is 10 seconds. So this is the time constant. So the time that takes to 63% of H steady state. Now in this case, H steady state is 10. Or whatever that variable is. This is a typical first order system. So if you want a very fast tank, you want to do what with your T? Are you increasing T or reducing T? if you want a fast tank? Reducing. So if you bring the time constant down, you're making the system faster. Can you see that? Okay. Now do the same calculation for the second system that we investigated. What was that? By the way, how do you take notes? Do you write it on tablets? What is your typical? You write it down? Most of you? Okay, so go back, look at the second example, and calculate the time constant. So we are going to do the same thing for our car. So what was the equation for the car? Let's go back and remind ourselves of that equation. It was this. The equation was dv over dt is 1 over m f minus cv. So for the car, the velocity over time was 1 over m f, which was the input, minus a constant times velocity. So what is the time constant? Again, the form is this. We want to have tx dot plus x being equal to u over b. So the equation becomes mv dot plus c times v is equal to f. So m over c v dot plus v is equal to 1 over c times f. So the time constant is equal to? So if you want to make a fast car, what can you do? Reduce the mass. That makes sense, right? Reduce the mass or? But what does this tell you? This tells you what? This tells you if you want to speed up the system, you have to actually you have to decrease the time constant, which is equivalent to decreasing the mass but increasing the drag. Does that make sense? Do you see that? C and M are, one is in the numerator, the other one is in the denominator. So this may be misleading here. It's counterintuitive to us that increasing drag would speed up this system. Doesn't make sense, right? So the first thing is, let's see if we made a mistake first, and then if we didn't make a math mistake, can we make sense of it? So did we make a math mistake here? Did I write the first equation correctly? And the format is what we want to get to. The second line is correct. So in order to get that to form, I multiplied both sides by m and moved the CV to the other part. And then in order to make the coefficient of x, which in this case is v1, I divided by c. So it seems like we didn't make a math mistake. So how can we make sense of it? That in order to have a faster system, I need to have more drag? So what do you guys think? Yes.
Does it have something to do with only reaching 63% of the steady state?
So that is the case. That the time is capital T is the time that it takes get to 63% of steady state. So yeah, that's by definition. But so it's also representative the overall time that it takes to settle down. So later on, we'll see the actual time that it takes to get to a steady state has a relationship with this capital T. So it's an indication of overall speed of the system. So what I think causes the confusion is the actual speed of the car is the steady state velocity that it reaches. So T doesn't have anything to do with the steady state velocity that it reaches. We can calculate that and see if the drag for that to be higher or lower, the drag should be higher or lower. So let's do that. Let's take away that confusion. What is steady state velocity? Let's calculate that. So we draw a line, separate. What is, so if V is known, what is V steady state? If F is known, M is known, and drag is known, the drag coefficient is known, what is V steady state? What is the method? How do we find V steady state? By doing what? From the model. So dropping the derivative term equal to 0. So we have F equals CV, which means V steady state is equal to what? It is equal to F divided by C. Which means what? The less drag you have, what is the consequence? Let's assume force is constant. So we're just keeping our foot the same on the accelerator. Yeah.
You have a higher velocity.
Yeah.
Correct.
So the less drag you have, the faster this car travels under the same effective load. That makes sense, right? So the model predicts if you reduce the drag, in a steady state, the car travels faster. Yes.
So, see if I have this right. So we have a set velocity that we want to get to.
Mm-hmm.
According to this, the time it takes to get to 63% of that is proportional to the mass over the drag.
Mm-hmm.
So don't you need that drag in order to balance out the forces and slow that car down, essentially? So that way you meet that specific velocity you're trying to get to?
That's exactly the reason. The reason drag plays this role that is counterintuitive is the drag is what causes us to reach steady state in the first place. So the more drag you have, the faster that transient would be over. Can you relate to that? The more drag you have, the sooner you get to that balance. That's the meaning of that. It has nothing to do with how fast the car will travel in this analysis. It simply says how soon that transient period would be over. That's it. Okay, so we calculated time constant for a car. What is the next example that we have to solve? It is the heat transfer system. So for the heat transfer system, we need to look at the differential equation in order to calculate the time constant. It was this equation. So the differential equation is Q dot is equal to 1 over M times C Q N minus H times A times theta. So the mistake I made so far is what? In writing the differential equation.
Theta dot, right?
This is theta dot, this is not Q dot. So let me correct that. And again, the form of the equation we're trying to get to is this Tx dot plus x is U input divided. So what is the time constant? The time constant for this system is M multiplied by C divided by H multiplied by A. So there are four variables that would define how fast this system would react, how fast this system will reach a steady state, in other words. Of course, by time t, we haven't reached steady state. We have only taken 63% of the road. But that's an indication of how fast the system responds. So if you want to have a faster heat transfer system, what do you need to do? What are the things that you can do? You can do four things. One is what?
Decrease the area.
You can, if you decrease the area, what will happen to T? T will go up, which means the system is slower. So if you need to increase the area, again, this is counterintuitive. It's like the drag. So it is as you intentionally try to lose more heat, but that's the key to a faster system. So both increasing H and increasing surface area would increase your heat loss, but it makes the system faster. And reducing the mass and reducing the heat capacity also will make the system faster. Any questions? Okay. Now, I intentionally didn't discuss another portion in the standard differential equation, first order differential equation model. What we stepped away, and now it's a good time to bring it, is that we talked about input to the system, but we never talked about unintentional inputs to the system, and that's a reality of life. And a very straightforward example is when we look at the car example. Okay, there's the force of engine, and there is the force of drag that we incorporated into our model, but there are other forces that either are out of our control or we can't have a deterministic way of calculating them. So for example, what would affect the velocity of the car that I can't properly calculate or count ahead of time for?
Friction.
For example, if the surface of the road changes, which results to change of friction, I have no idea of that. Okay? That is what an example of an input that does affect the system. It actually causes change in the response of the system, but it's out of my control. We call those inputs collectively disturbance input. So it will disturb the system, which is a signal that it's unintentional and unwanted. So it basically affects the system in that way. So for the fluid flow tank, if you're talking about a big reservoir, what is a U disturbance? So we have, for example, a river coming to a reservoir, and we have a way of, I guess, irrigating land downstream. So the output is also what physically leaves the system is known, or we can control it. But what we can't control is what? Rainfall. That's obvious, right? So rain falling into the reservoir, I can't calculate for it ahead of time, but it will affect the level of the reservoir, or evaporation for that matter. So these are other examples. So you get the idea of disturbance as input that is most of the time is unwanted, and it's but nonetheless is going to affect. So these are the examples that we already discussed. So what is U disturbance for each of these systems? We gave examples for each of these systems. Okay. Another way of characterizing the systems that we investigated so far is to call them linear time invariant systems. Linear, we discussed. Linear system is a system that when you double its input, the output would double. That's an indication of a linear system. And the way to have a linear differential equation is to have all the elements as linear elements. So no power 2 behavior, no square root behavior, power 3 behavior, things like that would not enter our differential equation. Now, the fact that a system is time invariant on the surface may be misleading. It doesn't mean that the behavior of the system doesn't change with time. That's why we are here. We're trying to predict and capture the time response of systems. What it indicates as and classifies these systems as time invariant is that the parameters of the system would not change with time. Example, let's look at this system. By now, you know it's a linear system. Now, what qualifies this as time invariant is the fact that A and C are not going to change over time. The parameters of the system are constant. That makes a system time invariant. Now, are all systems like that? It could be. It could. In most cases, it's not the case. It's not the case. Now, imagine the car case. What are the parameters of a car? Its drag coefficient in our model, and its mass. Is mass constant? You would like the mass to be constant, but it's not. How could mass changes? Mass of a car changes as you drive it. How? You burn fuel, so mass changes. You have 2 passengers one day, another day you have 1 passenger or 5. Do you see that? So we would like for, at least as we classify them, the systems are time invariant, so we don't count for variation of M. We don't count for variation of drag force. So if you're carrying something on the top of the car, of course the drag force changes. But our model is not equipped to take care of that. So I want you to be aware of it, that what we are doing is, of course, a subset of all possibilities, and that's that subset. So we are focusing on linear time invariant systems. Okay, so we discussed about linear time invariant. This is the frequency response. So how many of you have not taken mechanical vibration? So everybody had mechanical vibration. Is this familiar to you? What is the name of this plot? Make it larger. So what is this plot? What does it say? What kind of information does it carry? What was the whole concept of vibration? If you want to summarize it in one sentence, what does it teach? Or what do you learn in a course of vibration? So that's one tool that you always deploy. That's an intermediate step. But what do you get out of it when you're done with a system? What do you want to be able to predict? Yes. So you want to know how a system responds to what kind of input. Most of the time it's a sinusoidal input. So you want to know if a sinusoidal input comes to a system, how it will respond to it. That's the essence of vibration. So in a sense, we are also interested in that response. We want to know how systems behave if you have a non-constant input applied to them. So everything I said and showed you is a constant input. If you open the valve and leave it there, or if you just push the car at a constant level of engine force, or if you apply constant voltage to your system, a DC voltage. But what if that voltage is AC? What if it goes from a maximum to a minimum in a sinusoidal way? So what you see here is response of a typical linear time invariant system to that kind of input. Bode plot is a way of seeing that. Now, you can look at the response to single sinusoidal input once, and then go to another sinusoidal input and look at that response, and yet another one, and another one, another one. How many plots do you have to look at to get to the characteristic of the response? Hundreds. So the first one happened at 1 hertz, the second one at 2 hertz, the other one at half a hertz, the other one as 1/5 of a hertz, another one as 100 hertz. Do you see my point? Bode plot captures all of that information into a single plot. So on the horizontal axis, you have frequency. Frequency of what? Frequency of input that comes to your system. On the vertical axis, on each of these portion, you have one piece of information. At the top, you have magnitude of response. So if the magnitude of input is 1 unit, would the magnitude of output be 1 unit or 1/10 of a unit? That's what that upper piece shows you. It's the ratio of output over input in decibels. So it's in a log scale, so you can show a lot of variation in a single plot. On the horizontal axis, it's again frequency. At the bottom, it's a phase shift. So if you move your input at a certain phase, would the output follow, or would lag behind, or it would be ahead of your response? That's what that input shows. And hopefully we'll get to more. Any questions on what this is? So what does this tell you? It tells you, for a linear system, the ratio of input and output is constant at low frequency. And then as you get to a higher frequency, that ratio drops. So for all of these, the amplitude of input is the same. What changes is the amplitude of the output of the system. So up to a certain frequency, the output follows the input. After a certain frequency, it can no longer follow the input. So it doesn't show as much output. That's what the top pane of this plot shows. The fact that this drops down, let me write here, this is the ratio of output over input in log 10 scale. Multiplied by 20, that's the meaning of decibel. So if you forget that this is decibel, this is ratio of output over input. So to a certain frequency, that ratio is consistent. And after a certain frequency, it significantly diminishes, so you don't get as much output. And for the phase shift, it's the same. So this is the difference between phase of the output and phase of input. So initially, there is no difference. After a certain frequency, the output falls behind. So this is negative 90 degrees. So at high frequency, you see the difference in 90 degrees in phase, right? So if this is a sine, let me plot a typical sine wave. So 0, 90. So if you have 90 degrees of lag, it means that your input is here, but your output is down here. Can you see that? So this is 90 degrees. So if the phase of output is behind the phase of input by 90 degrees, which is the meaning of negative 90 degrees, means your input is here, but your output is trying to catch up. It's back there. That is the meaning of phase shift between input and output. Any questions? Okay. I'm going to finish by talking about now an application. It seems like modeling, at least to the extent that we discuss, applies to non-living systems. So we have circuits, we have tanks, we can heat transfer, we can have cars. Of course, these affect living systems, but they're not themselves living systems. The reason I've taken this blog from Scientific American is to show you the application of the methodology that we're learning here in other disciplines. This article is actually about drug development. What is the process of drug development? Essentially, I've tried to capture that process on this slide. So the slide basically says, in order to treat a disease, you need to know the mechanism of that disease. In other words, you need to know the dynamics of the system. And that by itself could be the major challenge. So you see that somebody gets a rash or has fever or has aches or an organ is failing or it's not functioning the way it's supposed to function. You see that. But in essence, you're just looking at the surface. You don't know what causes that. So part of it is to identify or come up with the mechanism, which essentially is your model. And then in order to affect that mechanism, you need to identify the protein that is going to affect that process. And now, once you have that process, now you're looking for a cure. You're looking for a medication. Now, a medication essentially is a bunch of molecules. So the process of drug development is the process of finding the right input to cause the output to do what you want it to do. Do you see that? Essentially, it's a control problem, but the majority of money is spent in finding the input that causes the output to behave the way you want. And here's the problem. The complication is this system is not single input, single output. So it's not that if you put a molecule, the output would change. There are multiple other inputs that are going to affect the system. So that's the whole concept of drug resistance. So at the beginning, one molecule may have some effect, but the body is not a linear time invariant system. It's pretty much a nonlinear time variant system. So our body adapts. And unfortunately, sometimes that system changes in a way that that input no longer has that effect on the output. So that's the concept of the drug resistance. So we are not going to diverge and start talking about biology. What I want you to know is that what we are learning here is not just applicable to engineering very solid systems. It's applicable in many, many places. In other words, differential equations and the information that it carries and the use of it is very widespread. So that's what I wanted to convey. Okay, please do take advantage of the resources on Blackboard. If you want to watch the lecture again I'm posting the videos, I'm capturing. The video basically essentially captures what is on the screen and my voice at the same time. So take advantage of those, and we'll have our first quiz at the end of this week. I'll let you know more details. Please stay on the subject. Thank you.